All right, guys, I'm on the top of page 2. So second page, right where we left off in class. What we are going to be talking about today is another discrete random variable probability distribution. And so remember yesterday we had a big discussion about the difference between discrete and continuous random variables. So I want you to think to yourself, why would in the 2010 NHL season the number of goals scored in a single game along with their corresponding probabilities, why would that be discrete and not continuous? So remember the difference between discrete and continuous. So for discrete, I can list all the goal options here, and the decimals in between these values do not make sense. It does not make sense to score 1.5 goals. You can either score 0 goals, 1 goal, 2 goals, 3 goals, 4 goals, whatever, but the decimals in between those values mean nothing. That is a discrete random variable. A continuous random variable is actually this example we're going to do down here when it has to do with weights. Because technically all of the decimal values in between each pound, for example, since we're talking pounds in this example, are relevant and they do make sense and they are there. They matter, okay? If I were to make a probability distribution for weights, can you tell me like how I would break up my X values? Like would I do like 20 pounds, 25 pounds, 30 pounds? There would be people in between those values, right? What if I did 20 pounds, 21 pounds, 22 pounds? There would still be people in between each of those values. So the decimal values for weights are relevant. Decimal values for goals do not exist. Okay, so discrete random variable, continuous random variable. Anyways, letter A, show that the probability distribution for X is legitimate. So this is a vocab word, probability distribution. It means this thing over here, this like T-chart looking thing. It is legitimate for 2 reasons. First of all of the values, all of the probabilities, I should say, are between 0 and 1. So let me actually emphasize that. All of the probabilities are between 0 and 1. You know what I mean. And the fact that all the probabilities for the entire distribution add up to 1. If they didn't add up to 1, then maybe we would be missing like 10 goals or something like that. But they all add up to 1. That means that this is the entire probability distribution. The probability distribution includes every single value for X. So apparently in the 2010 season, the minimum number of goals scored was 0 in any game, and the maximum number of goals scored was 9, and everything in between is, as you can see. Make a histogram of the probability distribution. So I went ahead and did it just in order to save time. Here's our number of goals on the x-axis. So the probability distribution, the x stands for number of goals. And we talked about how x in class yesterday, x in like algebra 2 means a variable, a number. And that's like the only answer for X, right? But in this case, in stats, X is a little bit different. X stands for number of goals, and it can take any of these values. So random variables, which we usually use the letter X or sometimes Y for, they stand for something different than what you have been taught about what X means in other math classes. So keep that in mind. X down here is number of goals scored. So I got all these different options between 0 and 9. And then I just labeled my y-axis. You know, as long as it's clearly labeled, you can choose different increments if you want to. But this is what my beautiful histogram looks like. And we can describe shape, center, spread, and outliers. You guys know how to do that. I do see a slight right skew. Remember, we've got a slight tail over here on the right-hand side. The center is probably somewhere around 2 or 3 goals. We could talk about mean or median here. We will calculate the mean down here. Median we could probably figure out just counting up to the 50th percentile, right? The spread, all of the teams score between 0 and 9 goals. We kind of already talked about that. That's talking about range. We could also talk about standard deviation if we wanted to, which we'll get to down here. Outliers, none apparent, none obvious. Letter C, what's the probability that the number of goals scored is at least 6? Another thing we talked about in class yesterday is the fact that it says at least 6. That means 6 or more, which is different from more than 6. At least 6 includes 6. If the wording would say more than 6, that would not include 6. So that part is really important to pay close attention to. Here's what we got. I'm going to do probability x greater than or equal to 6. That is the same thing as saying probability x greater than 5. So this inequality symbol is very, very important because we have the equal bar here that includes 6. So here's how I want to write it formally. Again, we're trying to have really, really clear, nice, precise, obvious work here to get the bump up and not the bump down. But probability that x equals 6 goals, that is right here in the t-chart. 7 goals, that is right here in the t-chart. All the way up, this is our grand total. Okay, calculate the mean and the standard deviation. We did this yesterday. I wonder if you remember how to do that in your calculator. Remember, you're going to put the number of goals in list 1 in your calculator, and you're going to put all of the probabilities in list 2. And then when you calculate the one variable stats, it's going to ask you where'd you put your data, and you're still going to type list 1. But then where it says frequency, that's the different thing, you have to put list 2. So you're doing one variable stats, and the x values are in list 1, and the the frequency, you have to change that to list 2. That is how to be successful in getting the mean and the standard deviation. It'll do that all at once. Remember the work that needs to be shown if you're going to write it, though. So remember how to find the mean. The mean of x, another way of writing that, as we talked about in class, is the e of x. It means expected value. That's when you take the first x value times its probability plus the second x value times its probability, and then work your way down. And remember, to show work for full credit, you can put the first 2 terms and then the 3 dots, and then the last term would be the 9 goals and the 0.001. When you crunch that number in your calculator, check it. Please do this with me. This is what our answer is, 2.851 goals. We expect a randomly selected team and a randomly selected game to score about that many goals. Did anybody score 2.851 goals? No, they didn't, because you can't score between 2 and 3 goals, right? But that decimal value gives us an idea that it's closer to 3 than 2. And in fact, we can use the standard deviation to help us interpret that even more. So remember the way that we wrote this in class on the previous example, we're starting with sigma x squared, because we do have to square root the answer at the end to get the number in your calculator. How do we show this work? You take the first x value, which is 0 goals, subtract the mean, which is right here that we calculated above. Don't forget to square it, and multiply it by its probability. Then move on to the next x value, which is 1 minus the mean squared times its probability. Do the 3 dots, and then the last term. That gives you this value. We do have to square root it. So one thing that you could do in your work is you could write square root of x squared and make sure you put a giant square root over all of this stuff. And then you wouldn't need to write this. You could just go right to this answer. But you do need that square root in there. If in your home screen, you're just going to start typing this, you're going to not end up with the correct standard deviation. So you have to have that square root in there somewhere. This is on the formula sheet too. I'll show you that in class next week. But remember the interpretation here for the standard deviation. We expect the number of goals scored by a team to differ from this number by about this many goals. So it tells us how far on average each team is from this many goals on average. Okay. Excellent. So there's just another example of what we did in class yesterday. The example we did in class yesterday was about what the GPA, or the A's and B's and C's, D's and F's, 4, 3, 2, 1, 0. Anyways, let's talk weights of 3-year-olds. The weights of 3-year-olds follow a normal distribution. Wow, I have this highlighted because that is an enormous clue that I'm going to use normal CDF in my calculator anytime I see that in the wording of a question. But that's kind of a blast from the past. We did that a long time ago. With a mean of this and a standard deviation of this, great. Randomly choose one of the 3-year-old females and call her weight X. So again, we're using this random variable X. And if I choose a different 3-year-old female, I'm going to get a different X probably, right? X just stands for the weight, and it can be any number corresponding to any of those people that we're weighing. Why is X continuous? Oh, I already mentioned this a little bit, rather than discrete, because it's weight, right? Weight is a variable that you can carry out to a bunch of decimal points, such that 2 people cannot weigh the exact same. Weights are not separated by gaps like the number of goals, 0, 1, 2, 3, 4. There's kind of gaps in between all of those integers. Weight is not like that. It is a continuous variable. So then how do we figure out the probability that someone weighs at least 30 pounds if I know this mean and I know this standard deviation? Okay, I'm a little confused. I'm starting to freak out. I feel like I can sketch this at least since they told me it was normal. Okay, the mean is 30.7. Okay, and the standard deviation was 3.6. I'm gonna go 1, 2, 3, 1, 2, 3. Where's 30? 30 is like somewhere right here. 30 looks like this, and it says at least 30 pounds. Okay, so do we include the 30 or do we not? Remember how, like, do we include the 6 or not is really important for a discrete variable? Do you remember how it's not important for a continuous variable because we're just concerned with the area, and the area of just one value doesn't really impact our shaded area? So the greater than or equal to or just greater than does not matter for continuous variables, just like it didn't matter in chapter 2. But yeah, I feel like I can do a z-score in all of this. Like, I remember how to do this. Let me see what I did. Let me erase this. So I first wrote the question symbolically. Probability x greater than or equal to 30. Convert that sucker to a z-score. Remember the z-score formula? The x value minus the mean divided by the standard deviation gives me this z-score. And according to my sketch, I knew it was just a little bit to the left of 0. Or of the mean, excuse me, which means I'm going to have a slightly bigger than 50% shaded area. I shouldn't have erased my picture, dang it, that's okay. How do I get this number again? Well, here's what you're typing in your calculator if you want to. Or you can look up this z-score in table A. Just remember that you're going to get a number less than 50 in table A because it's shading to the left in table A. So you have to subtract that number from 1 in order to get this number. But this is the probability of randomly selecting a 3-year-old. Okay, excellent. So what did we learn today, folks? Here is another discrete random variable with gaps in between all these x values, and we practiced with our calculator some stuff about expected value and standard deviation. And then we did a continuous random variable, which has nothing to do with these things up here. That is a review problem, which uses normal CDF. So we did a little bit of review, blast from the past, chapter 2. Love you guys. Thank you for watching. I'll answer questions as soon as you can get them to me. Love you all. All right, fam, welcome back. We are going to continue with our section 6.1 notes. I have a few things to point out. Again, just a little bit of review things and then some formula page stuff. Why do you remember the difference between mu of x and sigma of x versus x bar and s sub x? I bet you do, but just because it's going to be important for this chapter also, let's make sure we're all on the same page before we move forward. Mu of x and sigma x, those are parameters based on the entire population, which is sometimes difficult to know and find. And the whole reason why we don't use mu or sigma is when we cannot come up with information about the population. We're just basing everything on a sample. And that is when our symbols change just a little bit, where we use x bar and we use s sub x. So those are just statistics based off a certain sample, and they can be very variable from sample to sample. If I take a sample of 5 you guys and get your test average, that could be very different from a different sample of 5 you guys, right? And let me remind you, the P's go together, the parameter is based on the population, and the S's go together. These statistics are based off just a sample. Okay, here's some formula sheet stuff. Let me start over here with the chapter 1 thing. The very first formula on your formula sheet, you can take yours out if you want to and take a quick look at it, but is mu of x. That means average, right? And you already know how to do average. You don't need the stupid formula for it. But just remember what this formula is actually telling us. When I take the sigma, that means add up all of the things. X sub I is just a fancy way of saying all the stuff, all the people, all the data values. You're adding them all up and then dividing by n. You know what n is. N is the number of things there are, or number of people. And so how do I find S sub x? Well, or sigma. It just depends on if it's from the sample or if it's from the whole population, as you know. But here's how we find our standard deviation. I'm going to take the square root of, remember first I take everybody's individual value and subtract the mean. We did a little bit of this in our calculators earlier today and the day before. So you find everybody's deviation from the mean, and then you square all those deviations, which gets rid of all the negatives, because as you know, some people are below average, some people are above average. All the below average people technically have a negative deviation, right? But that's okay, we square them, and then we add them all up, and then we divide by n minus 1, and then we take the square root of the whole thing. And the reason why I have these highlighted in blue is because these use the sample size. That's what we talked about in chapter 1. And so how's that different from this chapter? A couple of you kind of inquired about this in class a couple days ago, but why are we not dividing by n or using the sample size in this chapter? So here we are in chapter 6. You'll notice we don't know the sample size. We don't know how many people there are. We don't know how many NHL games were studied. We don't know how many people are having a GPA calculated. But we do have all of these percentages, these proportions, right? So we don't have a sample size, but we have a certain proportion that goes with each of the x values. So now to find our mean, what we're doing is we're taking the sum and we're adding up all of the different x values. You know, the x values could be number of goals, could be the 4 for A, 3 for B, 2 for C. Those are the examples we've done in class so far. You take the x value you're given, multiply it by its probability, and do that for all of them and add them all up. So notice how there's no like dividing by n, because we're kind of already doing that by multiplying it by its decimal value of a proportion, right? And then same thing for the sigma. I guess maybe I should change this to sigma. Maybe I will do that real quick, just so it's not confusing. It's just an SX if it's from the sample. It is a sigma if it's from the population, but it's just so they match. Now it's changed. What I'm doing is I'm taking all of the x values and subtracting the mean and squaring them. But instead of dividing by the n minus 1, I'm again going to multiply here by its probability, because we're talking probability distributions here. So a little bit different than dividing by n minus 1, although the yellow highlighted part is the exact same. We're still adding them all up, but this time they get multiplied by each of their probabilities. And that is the difference between this chapter and what we did in chapter 1 with our basic stats knowledge. Okay, so there's a little bit of formula work for you, and now you have it in a nice safe place on your notes. Let's finish up this section by doing this piecewise function. Let's do a little blast from the past and take you back to Algebra 2, which for some of you was like 15 years ago. I get it. But how are we going to figure out how to sketch what this weird looking piecewise function is? I know some of you might be having some PTSD from Algebra 2, but that's okay. Let me show you how we can do this. I'm going to plug in, this is just a piecewise function. This is like a y equals mx plus b situation. It's just with decimals, so that's not a big deal. And then y equals 0.01, that, or 0.1, that is a horizontal line, my friends. That's like the easiest Algebra 1 linear graph that you can do. It's a horizontal line. And what does this tell you? It just gives you your endpoints for x. So what's the first x value I'm going to plug into this equation? I'm going to plug in 35. When you plug in 35 right here, you can do it in your calculator and you crunch this whole number, you get 0. My friends, my very first ordered pair on my graph is going to be at 0. So the x value is 35, the y value is 0. Now let me do, I don't know, I'll pick a number in between 35 and 45. Maybe I'll pick 40 just to help me sketch the stupid things. When I plug in 40, right here, I believe I get 0.05. There's my second ordered pair. When you plug in 40, you get 0.05. Check it with me. Pick a number between these two values. It's 40. Plug it in right here. You get 0.5. I love it. What about when I do 45? This is the endpoint right here. I'm going to plug in 45 right here. Plugging that in and then subtracting this, you get 0.1. And did you notice that since this is not a equality, it's just an less than, it's not a less than or equal to, that should technically be an open circle. Blast from the past on Algebra 2, you guys. I freaking loved piecewise functions. Okay, here's what the first function looks like. Isn't that nice? It is a line, y equals mx plus b, with this slope and this y-intercept, but only between these two x values. And at this x value, it's an open circle, and at this one, it's closed because there's an equal bar right there. Do you guys remember this from Algebra 2? Oh my gosh, I loved Algebra 2. Okay, and then what did we talk about this next piece? It's just a horizontal line at 0.1. Here's 0.1. So it's a horizontal line right here, but only between 45 and 50. Okay, cool. So at 45, I'm starting here, and now I get to fill in my circle because it overlaps. It's the same exact value. You plug in 45. You have nowhere to plug it in. The y value is 0.1, no matter what. You don't have to plug anything in. And same thing for 50. You don't have to plug it in. It's just a horizontal line right there. Here is what the piecewise function looks like. So for letter A, sketch the distribution as the variable continuous or discrete. Tell me this, are there gaps in between your x values, or can you plug in any freaking decimal point you want into the equation? Within reason, between 35 and 45, could I plug in 35.729 if I wanted to? Yes, this is a continuous variable. You can find a value of f of x for any x value, including all the decimals and fraction values. There are no gaps between the values. Okay, let's talk about letter B. What is the probability a student finishes in under 40 minutes? Well, what does my weird looking, this is kind of like a density curve. It's a weird looking piecewise distribution, but remember how usually we have like a bell curve and then we just draw our line and we shade? Well, this isn't a bell curve, but it's some sort of a curve situation. So I'm going to draw my line at 40. And it says under 40 minutes, so I'm going to shade this way. And I feel like I don't need normal CDF or anything for this because this is geometry. It's just a triangle. Don't you know how to find the area of a triangle? Area of a triangle is 1/2 base times height. So 1/2, the base here is 5. The height here is 0.05. Because this is 0.05 right here. So I just figured out 1/2 base times height. There's my area. Okay, that was weird. Easier than I thought. All right. What's the probability a student finishes within 40 to 45 minutes? So that would mean this purple area right here. That is a trapezoid. Oh God, now we're doing geometry. What is happening? Here's our trapezoid formula. 1/2 height. Base 1 plus base 2. Base 1 is this. It's 0.5. Base 2 is this. It's 0.1. The height is the distance between the two parallel sides. Be careful. The height is different if you measure it this way, depending on what x value. Height in trapezoids is always the distance between the two parallel lines. This is like SAT tips for you guys. Oh my gosh, so useful. Anyways, so my height is 5. One of my bases is 0.5. My other base is 0.1. I meant 0.05. And here is what that gives us. So yeah, you could also divide this into a square if you wanted to. Not a square, it would be a rectangle. And a triangle. You could do that also. Fun fact. Okay, letter D. What is the probability that somebody finishes in exactly 44 minutes, which is like right here? Exactly 44. Can't you argue that maybe nobody finishes in exactly 44 minutes? Because if you take it down to like the half a second, millisecond, nanosecond, then it's probably not exactly 44. Also, we don't have a shaded area there, right? We just have a line, and I don't think we can do a shaded area for a line. So you're exactly right. Nothing is exact for a continuous interval. If this was a discrete variable and I was asking about exactly 44 goals being scored, then I should be able to look at my probability distribution like that hockey example, and I should be able to come up with a number for exactly 44 minutes, but not in a continuous random variable, you guys. You can't do it for just one value. You need a shaded area. You need an interval. And continuous variables need intervals to be able to calculate areas. So remember, the base here would be 0. I just wrote a bunch of like notes here. Nothing is exact in a continuous interval. The base would be 0 and the height would be whatever this is, but you can't, like, there's no area there. That's just a line. Continuous variables need intervals. Okay, so that's kind of a weird example to finish on, but there it is. And now what I want you to do is start reading section 6.2, because we are going to do a lot of stuff about combining random variables next time I see you. Thank you for watching. Send me whatever questions you got. Can't wait to see you guys again. Love you.